Hello everyone, welcome to the Innovation Lab. In this video, we're going to be conducting an experiment to know if it is possible to build a solar-driven DC power supply, one that does not require battery systems as a power buffer between the solar panels and our load. Alright my friends, let's get started. The goal of the video is really to conduct this as an experiment so that we can know what could be the advantages or disadvantages on what could be the risks associated with doing something like this. And in the end, we'll kind of highlight everything for you guys. There could be some follow-on tests that we have to do in the future. This is only going to be the introduction to the concept. And our plan is to properly investigate this concept to know what we can do to make this more feasible, and also to be able to weigh the risks, to inform you guys of the risks, the do's and don'ts, and yeah, so we take it from there. So there's going to be a lot more in this series as we move forward in the future. I'm sure you guys must have seen all these free energy projects and videos all over the internet, some of them even on YouTube. I am really very careful on how I call anything fake because I don't know what they're doing. But if I am to be really honest, those videos and those projects end up being very misleading because they are not, you can't quite attain free energy using all those things that they are doing. But why those projects are kind of misleading is because they kind of tend to distract us from what we're supposed to be focusing on, which is the known free energy that is kind of looking at us every day. So we have this massive fusion reactor that we call the sun that gives us free energy every day. And instead of focusing on that, we find ourselves focusing on these people playing with spinning magnets. So I'm trying to kind of use this as my motivation going forward to focus more on solar projects. I know that all the components that we need to harness the power from the sun is expensive, but there could be ways around it. So in my videos, I'm going to be focusing a little bit. Is there ways that we can minimize the cost? Can we use affordable solar panels? Can we find used solar panels? Can we limit the amount of batteries that we need in our system? Especially if you live in an area where you get a lot of sunlight, how can we harness that? So essentially, my goal is going to be looking at how we can lower the cost of our solar energy projects, so that way it makes it more affordable to a lot of people. If we can go to a smaller battery size, if we can possibly, maybe in some cases, use ultra capacitors to harness the energy from the sun. What are the do's and don'ts? What can we do and what can we not do? What is feasible and what is not feasible? All right. Overall, the idea to conduct this experiment came from all the wonderful feedback and wonderful suggestions that you guys have been giving us. And this is why I kind of try to push for a constructive feedback from you guys, and I greatly appreciate it. So as you guys have seen in most of my videos, I kind of have a very big love for this very DC to DC boost converter, and I have featured it in a lot of my converter videos. The reason is because this converter, I think it's very well built for the price that you can buy it for. It's very affordable, it looks good, it performs well in my opinion. So I have been trying to use this, kind of leverage this design and leverage the affordability of the converter to try to use it for different things, where I have shown you guys how you can use it as a cheap and super affordable and very efficient battery charging system, and you can use it as, you know, to boost up your low voltage levels to high voltage level, and it works really well. I've also shown you guys how you can hack the converter to get more power out of it, and but overall, one of the things that I have always wanted to be able to do is to be able to show you guys how we can use this converter as an efficient low voltage to high voltage solar charge controller or solar battery charger. But lately I have had a wonderful idea which I'm going to show you guys in our next video. All the modifications, all the improvements, all the progress that I've made towards that effort. And I am super excited to share the success with you guys and to fully test this concept, because my solar panels coming in is going to be about 30 volts. I needed a battery system that required a charging voltage of about 40 something to 50 volts. So that way I can show you guys really that this system works, or even prove to myself that it works really well. But then I had an idea to use just the purely resistive load to test the ability of the converter to kind of deliver the energy from the solar panel to that load. And in the process of doing that, we're going to look at the efficiency of the system. So this is where all of this came from. And that made me realize, okay, we can also use this as an avenue to conduct a test to know if we can actually use a converter like this to, at peak irradiance, efficiently deliver power straight from the solar panel to our load without having a battery system in between acting as a storage device or as a power buffer. So in a nutshell, that thought is exactly what I'm going to be investigating in this video. All right, before we get started, let's go ahead and show you guys some of the prep work that we have done in setting up the 1.2 kilowatt solar array that we're hoping to use in conducting all the tests on this setup for you guys in the future. The goal is really to push about 1,000 watts of solar power going through this DC to DC converter, so that way we can look at the interaction between the converter and the solar array. But that made me realize that to be able to accomplish this at my target low voltage of about 30 volts, I needed a whole lot of solar panels connected in parallel. Luckily for us, I was able to access some affordable solar panels locally here. So essentially, all I had to do was to bring them in, make sure that I cleaned them up, and I kind of had to come up with a setup structure that will allow me to very efficiently connect the panels in parallel. To be able to connect all the solar panels in parallel in a way that guarantees an even power distribution between all the solar panels, I had to build a 6-to-1 paralleling cable that I needed using MC4 connectors that I was able to buy from Amazon, and some 8-gauge wires that I was able to source locally here. So that way, when I connect everything, it's just going to be 6 solar panels connected in parallel. And so I have just one positive and negative output from the solar panel array coming to the converter. So, and the reason for connecting everything in parallel was because my solar panels can go up to 30 volts nominal. Connecting those in series may give me a higher open circuit voltage that my converter may not be able to handle, because these converters are rated for a maximum input voltage of 60 volts. So I needed to really tie all the solar panels in parallel. So now, is it something good to do to connect a lot of solar panels in parallel? That's a subject that I'm really hoping to investigate in a future video. And if you would like to see that, also make sure that you stay tuned, make sure you stay subscribed to our channel. So I'm going to be conducting some tests to answer that question. Is it good to have multiple panels in parallel? Is it better to have them in series? I think it's almost a given that it's better to have them in series, but a big disadvantage to that is that you may end up with a higher voltage that your system cannot handle. Like in this case, I have 6 solar panels. If each one is putting out 30 volts, I'm going to end up with 180 volts, which possibly is going to fry my converter. So I cannot do that. So yeah, that's going to be a subject for a future video. I know that we connected all the solar panels in parallel, as I just mentioned, but we took a lot of precaution though. We made a lot of measurements. We made sure that everything is going to work well in parallel. The first precaution that I took was to make sure that I use the same exact solar panel, the same exact model and make of solar panels. I had to make sure that the open circuit voltage and the short circuit current of each solar panel is really closely matched. And as I was making the connection, I had to also remake the measurements. And as I connected them in parallel, I had to go check the leakage current going back to each solar panel to make sure that they are not super high and not concerning to me. So If you're going to be doing something like this, make sure you pay attention to everything that I'm talking about. If you connect a bad solar panel in parallel with a good solar panel, you may end up damaging all your system, because the bad solar panel is going to end up shorting your good solar panel, and that will not be good. You could overheat them and basically damage all the solar cells on your panels. So one of the adjustments that we needed to make on the converter, which was actually one of the things that one of our subscribers recommended, and I've done this in the past and it didn't give me a good result, but it works better with all the modifications that we've made. So that step is essentially to adjust the UVP setting of the converter low enough such that when we apply load, the solar panel voltage drops, but as long as it doesn't drop below the UVP setting, we're not going to get any oscillations at the input of the converter. So to do that, we dial down the UVP to about 21 volts. All right, so with the UVP adjustment completed, so right now we have an open circuit voltage of 29.5 volts coming in from the solar panels. So the next step really is to close the circuit breaker to bring in the power into the DC to DC boost converter. And as you guys can see here, we had a small voltage drop from 29.5 volts down to about 28.5 volts, and with the initial load we have on the system, we are seeing a current draw of about 7 amps going into the DC to DC boost converter. And looking at the output side, we are seeing a slightly boosted voltage level of 30.53 volts and an output current of 6.28 going to our load. So looking at our oscilloscope, we are seeing a switching frequency of about 25.6 kilohertz, which was what we set it to maximize the performance of the converter at this stage. So overall, what we are seeing at the initial power on testing phase is an input power of 199.5 watts and a delivered power of 191.73 watts going to our load. And that gives us an overall efficiency of about 96%. And if you ask me, I would say that is quite impressive. The next thing we really need to do is to try to apply more load on the system. And given that our load is a constant resistance load, so the only way we can do that is to slowly increase the output voltage of the converter with a target voltage of about 60 volts. And the next thing that we also need to do to ensure that we optimize the power delivery to our load is to make sure that the output current limit of the converter is set to the maximum point. All right. So with the output voltage of the converter increased, as we talked about, to help us maximize the load that we're putting on the system. So what we're seeing right now is an input voltage of 22.7 volts, which is a slight drop from where it was before, as to be expected, and an input current of 35.79 coming in from the solar panel, and that gives us an overall input power of about 812.43 watts coming in from the solar panel, and I think that's quite impressive. And on the output side of the converter going to our load, we're measuring a voltage level of 60.40 volts and an output current of 12.53 amps being delivered to our load. So when you do the math, we're getting an overall output power of 756.81 watts that is going to our load. And also now if you do the efficiency calculation, we're getting about 93.2% at this much load going through this converter. Again, I think this is quite impressive. We're not losing that much power, and I am highly impressed with the performance of this converter at this stage. Alright guys, and lastly, the final test that I wanted to conduct was to look at the temperature response of the converter overall, especially with no external cooling. And I purposefully did not add any external cooling fans because I wanted to see how much heat dissipation that's going to come out of the power inductor, given that we increased the inductance there. So overall, what we're measuring here is an average heatsink temperature of about 32.4 degrees Celsius. And for the inductor, we're seeing an average temperature of about 70 degrees Celsius, and that is to be expected because my goal actually is to kind of tune this inductor to act as a low value resistance that we're adding in series with the power that is coming in from the solar panel. And I'm going to be able to explain all of this in great detail in our next video. So I know that you guys will be wondering what were the modifications that we made to the converter to make it interact better with our solar panel system. So this is what I call the inductive reactance tuning. So essentially, we figured out a way that we can make some changes to the converter to better tune the input impedance of the converter to kind of match the output impedance coming out of our solar panel, such that when we apply a load, we get less oscillations at the input of the converter, and that allows that power handshake between the solar panels and the converter to be a lot more steady and a lot more efficient. To accomplish this, what I've done is to design a new power inductor with a goal of about 120 microhenries in comparison to the original power inductor that came with the unit, which is usually within the ranges of 25 to 40 microhenries. So that's a lot of increase in the inductance value. So overall, to be able to accomplish the input impedance tuning, we also added the ability to tune the switching frequency of the converter. So now couple that with the increased inductance of the power inductor, so we get a slightly higher input impedance, and this exactly is our goal. So if you picture it, it would be like adding a resistor in line with the power coming in from the solar panel, kind of a low value resistor. Overall, that's kind of our goal, and that was what we did. So in the next video, which really I'm going to be using this as a solar charge controller on a higher voltage battery system. So I am going to be taking the time to explain this concept. I'm going to take you guys through my design spreadsheet, going to explain everything, and I'm going to show you guys how I actually built the power inductors, so that if you guys want to do this in the future, you know exactly how to do it. And if you want to see that video, make sure you subscribe to the Innovation Lab so you get notified as we release that video. So this video is not going to be complete if we don't talk about the advantages and disadvantages of running a battery-less system like this. So starting with advantages, as you guys can see on the test setup, we don't have any battery systems or storage devices here. So that actually makes the whole experiment a low-cost experiment or a low-cost concept. Also, another advantage is that the converter that we're using here is a very cheap converter that you can buy for about $25 or even less. And the modifications that I've made here is something that you guys can also implement. In my next video, I'm going to go in depth to explain everything so that anybody can really implement all those changes. Also in the future, one of the concepts I want to experiment is to see if we can use a smaller battery pack or even a supercap to act as a power buffer between the solar panel and the rest of our system. And that could be more important if we are considering driving high storage loads in the future, or possibly adding a power inverter to the setup. All right, so let's look at the major disadvantages of running a battery-less system like this. First of all, as we would expect, this means that we don't have an energy storage device on the setup or on the system, so you can only use this during the daytime. And secondly, this may not be the best idea if we're considering applying loads that may present high storages or high inrush currents on the system. Another disadvantage of a system like this, from what I've seen, is that you only get the maximum power from the system at peak irradiance, which is right around 12 noon to about 3 p.m. depending on your location. And lastly, so this is something possible that could happen. So you could possibly overload your solar panel, especially if you're not careful with your calculations, especially if you're not paying attention to how much load you're putting on the system. So you could damage your solar panels as a result of maybe high inrush currents, as we have talked about. One of the disadvantages of paralleling a system like I've done in this video is that you could also damage your solar panels, and I will make a separate video to talk about this if you're not careful how you design or structure your solar panel array. So this could lead to a damage, and I plan to investigate this further into the future to explain it more to you guys. Alright, so that's it for this video. I hope you guys had some fun. I hope you learned something from the video. My intention was to run this as an experiment kind of driven out of curiosity to know if this is actually something possible. And from what we have seen in the video, the modifications we made on the converter gave us a best case efficiency of about 96%. Our initial goal was to see if we can push up to 1000 watts of pure solar power going through the converter being delivered to our load. And from what we're seeing, we were able to get close to about 800 watts being delivered to our load. In my opinion, I would say that is success. Alright guys, again, I hope you guys had some fun watching this video, and in the next video we're gonna dig into actually using this system as a solar charge controller, and we'll see how much power we're gonna get out of it. And if you'd like to see that video, don't forget to subscribe to the Innovation Lab, and if you found some good value watching this video, don't forget to give it a thumbs up. Alright my friends, I will see you guys in the next video.